Welcome all. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad, and I am covering the lectures for microprocessor and microcontroller subject with code KEC 502, which is being taught in 5th semester. So nowadays I am covering with the Unit 1 and currently I am teaching instruction set. So in previous lectures, I had already covered the data transfer instructions, arithmetic instructions, logical instructions. So today I'll be covering branching instructions. So let's understand these instructions one by one. The branching instruction alters the normal sequential flow. That's why they are known as the branching instructions, because they branch from the current execution sequence to another execution sequence. So these instructions alter either unconditionally or conditionally. Means that these instructions allow the users to branch to other instruction conditionally or unconditionally. See how? So under the unconditional branch, it goes to the new location no matter what. And when we talk about the conditional branch, it goes to a new location if the condition is true. So the first instruction is the jump, JMP. Operand is 16-bit address. And description is jump unconditionally. So when we write JMP, I am taking this example only, 2034H means as soon as I encounter this instruction, the program flow will go to this memory address. This is the memory address. And there is no condition. In any of the condition, the program execution will go to this memory location. So the program sequence is transferred to the memory location specified by the 16-bit address given in the operand. Now, next is jump conditionally. So, in the previous slide, we studied about the unconditional jump. Means the program execution will be branched no matter what. But in this case, the program execution will branch to some other location conditionally. What will be the conditions? Let's see. So, the format is this: J, some condition. This alphabet is denoting some condition. This is the 16-bit address, jump conditionally. How? Suppose JZ2034. Yes. First of all, we have to understand this, that the 16-bit address given in the operand, the program execution is transferred to this address based on the specified flag of the PSW, that is the program status word. So replace X with some condition. Z denotes some condition. What condition? 0. Means if the Z flag shows the set condition in the PSW, then the program control will jump to 2034. Means if the Z flag is set, then the program control will transfer to this address. So these are all the conditions. This was just an example. Replacing X with Z was an example. So other conditions are JC means the program execution will jump to the given memory location if carry. If carry means if the carry is set. Next is JNC means the program control will jump to the given memory location if carry is not set. Means carry is 0. Next condition, the program control will jump to the given memory location if number is positive, if the result is positive. P stands for positive, means the sign is 0. Next condition, the program control will jump to the next memory location if minus, means sign flag is 1, if the resultant is in negative. Next, the program control will jump to the next memory location if 0, same as the example studied in the previous slide, means Z flag is set. Next, the program control will jump to the next memory location if no 0, means the 0 flag is reset. Next is, the program control will jump to the next memory location if parity is even, means if the P is 1. And the last, the program control will jump to the next memory location if parity is odd, means the P flag is reset. So we had already studied all these conditions when we studied the flag register during the architecture. Yes. So all the conditions of the jump statements are dependent on the flag register only. Next branching instruction is call. Operand here is 16-bit address. This instruction is unconditional call. So we will now try to understand the difference between the call and the jump. The program sequence is transferred to the memory location specified by the 16-bit address given in the operand. So this thing is same as in the jump statement. Okay. Before the transfer, what is the different? Let's see. Before the transfer, the address of the next instruction after call, the contents of the program counter, means the contents of the program counter is pushed onto the stack. Yes. And at the end of the means, suppose call 2034, this is the address. So when this statement is encountered, the program control will go on to this address. At this address, certain module is written. At the end of the module, return statement is written. So what will happen? When this instruction was encountered, the address of the next instruction, the address of the program counter got transferred to the stack. Yes. Yes. So the program counter contents are stored on the stack. Yes. Now, after executing the return, after the return is encountered, now these contents are popped out. Yes, these contents are popped out, and again the program counter holds this value. Yes. So in this way, again our program control will get back to the main routine. So this is the difference between the call instruction and the jump instruction. In jump, there is no provision to come back to the main routine, but in call instruction, there is a provision to come back to the main routine when the return statement is encountered. Now, call conditionally. So, the call instruction also contains the condition. Again, in this case, CX, X denotes some condition, 16-bit address is the operand. So, program sequence is transferred to the memory location specified by the 16-bit address given in the operand based on the specified flag of the PSW. Again, the condition is dependent on the contents of the flag register. So, again in this case, before the transfer, address of the next instruction is pushed onto the stack, and after the return statement is encountered in the call instruction routine, then the contents will again be popped out and the program counter will be updated and we will get back to the main routine. So, example is CZ. Again, this instruction will take the control of the main program to this new address if Z flag is set. So again there is a condition. Other conditions are call if carry, same as in jump. Call if no carry, that is the carry flag is reset. So in case of call if carry means the carry flag is set. In call if no carry means carry flag is reset. CP means call if positive, means sign flag is 0. CN means call if minus, means sign flag is 1. CZ means call if 0, if 0 flag is set. CNZ means call if not 0, means 0 flag is reset. PE means call if parity is even, means parity flag is 1. Call if parity is odd, means parity flag is 0. So in this way, all the conditions are dependent upon the flag register. So next instruction in this category is RST 0 to 7. Restart. These are also mentioned as the software interrupts. RST instruction jumps the control to one of the 8 memory locations depending upon the number, depending upon this number. Yes. So there are basically 8 restart instructions. RST 0, RST 1, RST 2, 3, 4, 5, RST 6 and RST 7. In this way there are 4 RST, that is the restart software interrupts. So these are used as the software instructions in a program to transfer the program execution to one of the 8 locations. So suppose example is RST 3. Yes. So how will this instruction understand to which location it has to transfer the program control? Yes. So let's see how. This is the address table of all the restart instructions. Suppose it says RST 0, means the 0 will get multiplied by 8, it will give 0. This is the decimal number and you have to convert this number into hexadecimal. Again, for 1 into 8, 8. Again, this is decimal and you have to convert it into hexadecimal. RST 2, we have to multiply 2 by 8. This gives 16 in decimal and we have to convert this number into hexadecimal. Again, 3 into 8, it gives 24. Again, this number has to be converted into hexadecimal, it gives 0018H. Similarly, all these numbers can be used to calculate the addresses. Which address? To which the program control is to be transferred. That is a restart address. Next instruction in this category is NOP, that is a no operation. Operand here is none. That is the NOP means it is having the implied addressing mode. No operation is performed. It means no operation is performed. Instruction is fetched and decoded but no operation is done. Usually it is used for delay or to replace the instructions during the debugging. So in this way this instruction can be used and this is the machine control instruction. HALT. HLT stands for HALT. There is no operand to be mentioned. Again, this is following the implied addressing mode. The CPU finishes executing the current instruction and halts any further execution. When this halt is encountered, the CPU finishes executing the current operation. An interrupt or reset is necessary to exit from the halt state. So in this way, we can come back from the halt condition by using a reset or the interrupt. Machine control instructions. Another instruction in this category is TI, that is the interrupts disable. Yes. The interrupt enable flip-flop is reset and all the interrupts except the trap are disabled. No flags are affected when this instruction is executed. Again, when EI is executed, the interrupt enable flip-flop is set and all the interrupts are enabled. So, no flags are affected. This instruction is necessary to re-enable the interrupts except trap. Next instruction is RIM. So, this is a multi-purpose instruction and used to read the status of interrupts, all the interrupts. The instruction loads the 8 bits in the accumulator with the following interpretations. So, whenever this instruction is executed, then automatically when this instruction is used to read the contents of the accumulator, means when we read after executing this instruction, when we read the contents of accumulator, the contents of the accumulator will be interpreted as shown here. The first D7 bit shows serial input data bit, D6, D5, D4 shows the interrupts pending bits. Then IE means interrupt enable flip-flop is set if this bit is 1. Again, these 3 bits shows either the interrupts are masked or not. Last instruction is SIM instruction. This is a multi-purpose instruction again and it's used to implement the interrupts. Means it's used to set the interrupts masks. And how it is done? First of all, we will transfer this value, whatever value we want to give to these bits. This value is to be transferred to the accumulator and then this instruction is executed. After giving the value to the accumulator and executing this instruction, the accumulator contents are interpreted as follows. First bit is for serial output data. Second is for the serial data enable. If it is 1, then the serial data transmission is enabled, otherwise not. Next, this is undefined. RST 7.5 D4 bit, it reset the RST 7.5. Again, mask set enable. If this bit is 1, then only the mask set is enabled, otherwise not. Again, these 3 bits are used to mask bit interrupts 7.5, interrupt 6.5 and 5.5 respectively. So, these bits are used to mask these interrupts. In this way, the RIM and SIM instructions are used to read the interrupts status or to set the interrupts status respectively. So, these were all the machine control instructions. In the next slides, we will move on to another interesting topic, that is interrupts in details. So, that's all for the day. Thank you.